Okay? And this is relatively easy to understand. It's essentially, again, you're looking at the sun here, moving in an arc. It is just the angle that the position of the sun in the sky makes with respect to a horizontal plane. Okay, so this is the plane, the green plane here is the plane at which you're standing, let's say right there on Earth, and that's the plane that is tangential to the Earth's surface. That's this green plane, okay? And when I play this, it make more sense. So you can see this angle here is the elevation, okay? So let's repeat that. This angle shown by this red curve here is the elevation. It's measured with respect to the horizontal plane. Okay, one more. Okay, that's the horizontal plane. Goes all the way to the top, and this is referred to as solar noon, which is when the light is as high as possible in the sky. The sun is as high as possible in the sky. Of course, that changes with the time of the year versus whether it's summer or winter. We won't worry too much about that for the purpose of this class. And again, that's the angle. So that's referred to as elevation. Okay, so the elevation, it's also referred to as altitude angle, is the angular height of the sun in the sky measured from the horizontal plane. Okay, now once we have the elevation, let's think about the Earth itself. So it's shown here. Okay, and sunlight's coming in, and this is a particular time of the year. Let's say in this particular case, it's summer in the northern hemisphere. So the axis is pointing towards the sun in this direction. And this delta, by the way, shown here, which is the angle of the axis of the Earth relative to the vertical, the plane that's perpendicular to the sunlight, which is coming here, is called the declination angle, or delta. Okay, and of course this changes with the time in the year as the Earth rotates around, revolves around the sun. This changes, right? This rotates back and forth. Okay. So in other words, in the winter, of course, this goes this way, in the summer it goes this way, and so on and so forth. Okay, so and it's the same angle here, where this orange dashed line shows the line that's parallel to the sunlight. Okay, axis parallel to the sun's rays. Okay, so the tilt of the Earth compared to the sun is given by the declination angle. It depends on the season. This is shown here is the maximum declination angle occurring at summer solstice in the northern hemisphere and winter solstice in the southern hemisphere. So there's a typo right there. Okay, so the next angle to keep in mind is what's referred to as the zenith angle, or zenith angle, okay, zeta, which is measured, let's say you're at a particular location on the Earth, which is, let's say, right there. If you draw a normal to that surface, so here we are assuming the Earth is a perfect sphere. So if you draw a line, a radius of the sphere from the center to the surface here and extend it out, that's a normal to that surface. It is the angle that the normal to the surface makes with the rays of the sun. Okay, it's referred to as the zenith. And of course, zenith is essentially phi minus delta, whereas phi is this the latitude, right? The latitude of the position on the Earth is the angle of this radius with respect to the equator, which is shown right there. Okay, so we'll see how these things affect orientation of the panels later on. So for instance, in Salt Lake City, we are here, the latitude's about 41 degrees north, something like that. Okay. Another angle to keep in mind is what's referred to as the elevation angle, which is exactly what we saw before, which is basically, again, this is the sun rays coming in, and this is the angle with respect to the horizontal plane that's tangential to the location on the Earth, which is exactly what we saw before. So that's the same elevation angle. Okay, so elevation angle plus the zenith angle is 90 degrees, right? Because it's just this two lines, this normal and this tangential line. And you can also see all the other relationships. For instance, the elevation angle referred to as alpha is 90 plus phi minus delta, where this C is the latitude, which is the total angle here, right? This latitude, as we saw before. Again, you don't need to memorize any of this. You can always look it up, like I said. We don't have any closed book exams. Okay, so those are the three angles. Again, just to recall, we have the declination angle here, we have the zenith angle here, and we have the elevation angle here. So three things to keep in mind. So if you think about, if you're trying to align your collector, whether it's for solar pasteurization or desalination or whatever, you need to know these three angles in order to be able to either track the sun or be able to align the collector in the best possible manner. So for instance, if you think about it, if you don't want to track the sun, you need to be very careful how you align it, because you need to average over all possible angles during the day and during the year to get maximum collection efficiency, right? Because if you're not tracking the sun, you want to pick the best orientation to get the most energy out. And we'll talk briefly about this, but this is something we should be very aware of. And it can make a huge difference in terms of the total energy output that you can get. Okay, and there's some examples here of calculation of how you can use this at sunrise, sunset, and so on. Not terribly important for us, but it's useful to know, for instance, for your project. Okay, so the next concept to keep in mind is the azimuth angle, which is actually quite simple, which is essentially if you take a compass and point it, and of course the arrow, the compass points north, it is the angle that this arrow, for instance, the north-south direction, makes with the position of the sun. Okay, that's the azimuth. So again, it's the compass, azimuth angle is the compass direction from which the sunlight is coming. So you can see it in this animation. As the sun moves, the azimuth goes there, goes to 0 degrees when it's at the highest point in the sky. It's pointing right north, if you're at the equator. And then it moves down, goes the other way. Okay, so the azimuth angle simply goes up and then goes down. Okay, so pretty simple there. But it's very useful. So you need to know the azimuth angle. It tells you with the azimuth angle and the elevation, you know exactly where the sun is relative to the position where you're placing a collector. Okay, and of course there are equations here which relates the azimuth angle to the declination and the latitude, for instance. Okay, not terribly important for the purpose of this class. Just I want you to essentially have an intuitive understanding of what's going on to the sun with respect to where your collector is, because that's important. Okay, then there are a few other topics here which you're welcome to read through because it gives you some additional information. But for the purpose of the class, we'll skip to this. This is the last concept that I need you to understand, which is something we've seen before. Essentially, what happens when the sunlight hits a tilted surface, right? So let's say the sun is here. That's the solar array, and that's the horizontal plane of the Earth. Sun rays are coming in, and if it's coming in exactly normal, that's our best case scenario. You'll collect the most energy. But if it's coming in at an angle, say it's a little bit like that, then you have to take into account the cosine theta loss in energy, right? So typically the way people look at it, also just a different way to look at the same problem is you look at the normal to the panel or normal to the horizontal. So that's referred to as the S module and S horizontal. And how far away is this S incident, which is the rays of the sunlight, from these two normals? Okay. And here's a nice animation which basically shows the same thing. So that if you can change the elevation of the sun here, so the sun's moving higher and higher up in the sky, you can see it gets so this is the ray you should be looking at, right? And you can see sorry, this is the normal. This is the ray you should be looking at, the red one. It changes angle as you go down, and of course you want this to be as close to the normal as possible. Now, if you are like that, right? Let's say the sun is coming in at a angle like that, let's say, which is the elevation. you can change the angle of the panel in order to match it, right? And that's referred to as tracking. So now you're tracking the sun, and the green and the red lines are matching. Okay, and that takes some energy, right? Because you need to move the panel in order to track the sun, and we'll talk more about that. Now, the impact of all this can be seen in this curve, which is actually a very, very useful and important way to visualize what's going on. So this is a very, very useful thing to keep in mind. So let me take a few minutes to explain what this plot is. So first of all, the horizontal axis, you see the day in the year, right? Goes from 1 to all the way to 365. So that's the day of the year. Winter, summer is in the middle here, and so on. Okay. The vertical axis here shows the direct radiation from the sunlight. So remember in the last class we talked about direct and diffuse sunlight. Here we're only considering the direct sunlight. So keep in mind in all these analysis we're talking about, we're only looking at direct sunlight. In other words, you're only looking at the rays that come straight from the sun, right? Not the ones that are scattered off the clouds and so on and come at different angles. We will talk about those later on. It's not particularly relevant when you talk about tracking the sun. So that for that purposes, we're only talking about direct radiation. Again, it's in units of kilowatt hours per meter squared per day. Kilowatt hours, for some of you who probably are familiar with this, just energy. Right? So this is total energy. Watt hours is watts is power times time is energy. Energy per unit area per day. So it's averaged over the day. Okay. Okay, now let's see what these three plots are. First, the blue curve is the incident power, which is coming from the sun. And that's basically doesn't change, right? That's this curve. Every day, roughly, you'll get the same thing. In the summer, maybe you get a little bit more. In the equinox, you're a little bit closer to the sun, so you get a little bit more. Other than that, pretty flat. If you don't track the sun and you simply put the panel on the surface of the Earth, so it's horizontal, which is the red curve. This is the power on the horizontal. Okay, and that's what you will get that. So because the sun is again, remember this is averaged over the day. So the daily motion is already averaged. Here you see it goes down, right? Because when the sun is at a steeper angle, you lose some energy. It's shown here. And this is what happens if you actually, the green curve is what happens, what you produce in the module when you are at a certain orientation of the module. Okay, and you will see that. And that's not good, right? This is very bad, actually. And that's the array tilt here that we can change. 45 degrees is what it is right now. So if you're at a latitude of 0 degree north, like you are in Singapore, for instance, which is right on the equator, you would not do this because you lose a lot of power. You want to change that tilt angle to match that blue curve as best as possible. You would, and the best you can do in this particular case is put straight on the horizontal, right? Because the latitude is 0 degrees. Now let's see, and you can change this. This is obviously a Java applet. You can change it pretty easily. Now, you can change the latitude. Let's change it to Salt Lake City, which is about 41 degree north. Okay. So actually, I just looked it up. So it's 41 degrees. Okay. Pretty easy. So you can change that. Now you look at the blue curve. It has changed, right? It's different. So see what's happening to the blue curve, which is the incident power. It is flat when you're at the equator. When you come north, more north, let's say Salt Lake City, you expect to see this. In the winter months, you get less energy. In the summer months, you get more energy. In the equator, there's no big difference between winter and summer, which is why the blue curve is flat. Right? And this gets accentuated as you go further and further into the poles, right? Like that. Okay, so let's come back to Salt Lake City and now try to figure out, okay, what's the best we can do in terms of the orientation of the array. If the array is flat against the ground, the red and the green curves overlap and you get this, which is okay. It's not so bad, but you can do better, right? Of course, this is what you are trying to get. You're trying to get it as close to this blue curve as possible. So let's see what happens as you change this. So you're going to tilt the array. The green curve starts getting higher than the blue curve. right? So you're getting more energy because you're orienting the array better. Remember, Salt Lake is in the northern hemisphere, so when we talk about array tilt here, this is pointing south. Okay, so the array is pointing south. And keep going, keep going, keep going, keep going, keep going, keep going, get better and better and better and better and better and better, right? And then suddenly you see something strange happening. So up to here, you've peaked here, and if you start tilting it more, you see this starts going down. Okay, so in other words, during the summer months, you start losing some of the peak power. In the winter months, you can still improve, right? And if you keep going, you end up with something like this. You start saturating out here. There's not much difference, but you can gain quite a bit in the winter months. So again, it depends on the application, what you're trying to do. When you keep going, of course, you lose, right? At some point, you go back to this. So you can, there are many ways to optimize the array angle. The way I prefer, for instance, would be to average not only per day, but average over the year. So you average this, you take the area under this curve and try to maximize the area under this green curve and try to maximize that number, which I assume will be something in that order, something around here. Okay, so the people who install solar panels, for instance, do this in a much more careful and very, very highly detailed simulation over many years data, and they also, of course, try to plan for other things like cloud coverage and things like that. But this is a good example of why we need to know the location of the sun relative to whatever collector you're using. So also, I should reiterate that this is important not only just for solar panels, but also for anything that collects the sun, right? Collects sunlight. So for daylighting or water pasteurization or desalination, whatever it is, this knowledge can help you improve the performance. Okay, so so I highly recommend you go and play with this. It gives you some interesting details, and especially some of the equations that would be useful when you try to model the performance of your system as a function of daily motion of the sun or seasonal variation of the sun. Okay, so now let's go to the lecture on the basics of thermodynamics. I'll stop for a few seconds and see if there are any questions. Are there any questions before we change topics a little bit? Okay, guess not. But let me just reiterate that when you do the analysis for the systems that you are working in your team projects, it's important to not just think about the sun as just a fixed light source, right? It's changing every day and it's changing over the year, which means that you actually do need to model how your system will perform as a function of hour in the day and the day during the year. And that's the main reason I went through that those slides, okay, and the last lecture. So it's very important that you're able to model it, and it's not hard. You can simply write some very simple code in MATLAB to do these calculations. Okay, so the goal for today, it's a relatively short lecture, and the goal is to understand some of the basic concepts of thermodynamics and how, and only those concepts that are relevant to us for solar cells or solar thermal devices. I refer to solar thermal devices, but they also are applicable for photovoltaics, as we will see in some of the subsequent lectures. Here we will focus primarily on heat engines, okay? So what is a heat engine? We talked about what a heat engine is briefly in some of the previous lectures. A heat engine is just a machine that converts light or fuel to heat. Okay, well, it doesn't need to be this particular thing. A heat engine can be anything that converts energy from one form to another. Okay, that's a general term. But for us, we will think about anything that converts sunlight or fuel as you're heating it, or even heat directly to work. And this heat can refer to work which can be mechanical, which can be electrical, it can be, again, heating, whatever. Okay, this can be, it can take many different forms, right? Which is, okay, so so here I say the heat which is then converted to motion electricity. So if you think about the whole thing, we have an input, which is light, fuel, heat, and an output, which is kinetic energy, electrical energy, or something else. And the most primitive way to think about this is a steam engine, right? This is an example of a very simple heat engine. You have a heat input, it heats up the water. That's a hot part of the heat engine at temperature T1. The water becomes steam and it condenses at the cold part of the heat engine, which is T2. Because the steam expands, it pushes a piston, as shown here, okay? And that piston essentially turns a wheel, okay? So that's the work output, moving wheel. So from a thermodynamic point of view, you have a heat input going into the system. You have a hot and the cold region, which becomes very important in the subsequent concepts. And then we have some work that's done. Okay, and then there's some heat that's dissipated, some lost heat, because the steam will condense on the cold part and become water again. So that's some lost heat here. So it's a heat input, work done, and a lost heat. Now, if you think about conservation of energy, all of those needs to match up, right? The heat input must be equal to work output plus whatever heat is lost. And that's essentially the first law of thermodynamics. Okay. So we can generalize this idea in a very, very simple fashion by thinking that there is two distinct points here. One is T1 and T2, and their difference in temperature. And essentially, this is a particular example of something taking advantage of this difference in temperature to generate energy. Okay, and we saw this, for instance, when we learned about refrigeration, right? So this heat difference is used to generate energy. And you will see that almost all cases, this is how one would utilize sunlight or any form of energy to do work. And the examples are numerous. We have coal plants, nuclear power plants, solar thermal plants, geothermal, thermoelectric devices, etc. All the energy conversion devices can be thought of this way. Let's look at the most common one, which is somewhat relevant to us, but it's useful to think. It's the internal combustion engine. So the way this looks like this, so it's essentially a cylinder, and it's not necessarily directly related, but it's useful for us to understand the trade-offs and the key constraints involved. Okay, so this is a 4-stroke cycle. Of course, there are many different ways to implement this, but first you have a process called intake, where the air-fuel mixture is drawn in. So here, the air and the fuel is drawn into the chamber. This is the chamber, combustion chamber. Okay, and here's a piston. Okay. So, the exhaust valve in this case is closed. You have a spark plug, which we'll come to in a second. And that's the intake valve, which will close in a second. The piston, of course, is connected to some engine here, right, which is shown as a crankshaft and so on. Not so important for us. The next step is the compression. So then this thing turns, and the piston essentially compresses the gas, and all the valves are closed. Right? Nothing can escape, so the gas is simply compressed. So you have a lot of potential energy here right now, right? Because the gas has huge amounts of potential energy at this point. The next step, you have an explosion, which happens because of the spark plug. Okay, so it's power. The explosion essentially produces energy, which causes these gases to expand rapidly, which pushes this piston down. Okay, so this piston goes down, and you start turning. All the valves are closed. So here you're starting to increase your volume because of pressure. The pressure is very high, so you have to relieve that pressure by increasing the volume, which forces this to move. So that's the work that's done. And the last step is exhaust. Basically, the exhaust valve opens and the exhaust gases go out. Okay, and the whole process repeats. So that's again an example of a heat engine. Where you have a cold part where the explosion happens, and a hot part and a cold part where the exhaust gases leave. In this case, they are not necessarily separated so much in space. Okay, so those systems are essentially generalizations of heat engines, but for us, the most important ones to think about are direct conversion systems, where the light is directly converted to electricity, which is photovoltaics, or the light is converted to fuel, and then the fuel is converted to some energy, motion, electricity, and so on. Of course, light to fuel is essentially photosynthesis, right? Everyone knows this. And fuel to motion is, internal combustion engine, for instance. So examples of photovoltaics, photosynthesis using biofuels, hydro, wind, tidal, etc. Now, of course, we will be very concerned in this class about conversion efficiencies. In other words, how efficiently can you take energy in one form and put it in another form? So it's very useful to think about energy as different grades. There are, of course, energy is the same, but some forms of energy are more useful than other forms, which is why we use electricity, right, to light our homes and heat our homes and so on, as opposed to using heat, thermal energy, for instance. In other words, we don't have a natural gas plant for each house. You have a huge central natural gas plant which creates electricity, which is a higher grade of energy, and that electricity, which is a higher grade of energy, can be transported everywhere, right? Another example is fuel, right? Gasoline is a very high grade of energy because it can be transported. It's a very high density of energy. It can be transported relatively easily everywhere. So these things are considered higher grades of energy. So you usually, most engines, in a way to think about it, is you take energy from a high grade and you convert it to energy or work at a lower grade. So electric generator, for instance, takes mechanical energy. So this is just the opposite. Mechanical energy and creates electrical energy with efficiency for 80%. Of course, efficiency is never 100%. As you will see, there's quite a bit of losses involved, and we are very concerned about these losses, clearly. Electric motors come from electrical to mechanical with efficiency over 90%. Light to heat, sunlight, let's say, for heating is greater than 90%. Chemical to heat, chemical essentially refers to fuels, can have efficiency over 90% as well. So these can be quite high, but of course these are theoretical limits. In actual practice, it's significantly lower than these. Okay, so to understand where these theoretical limits come from, we need to understand a few fundamental ideas in thermodynamics. First, there is a limiting efficiency as you go from heat to mechanical energy, and this is referred to as a Carnot efficiency limit, as we will see in the next slide. This goes as 1 minus the ratio of the temperature. So as I said before, every heat engine has a hot part, it's the temperature of TH, and a cold part with the temperature of TC. So 1 minus TC over TH is the best possible efficiency that one can hope to achieve. And we'll come back to this. Examples, of course, are heat engines, solar thermal. You can also have other limiting factors, like when you go from light to electrical energy, for instance, in photovoltaics, you have not a Carnot. You also have a Carnot efficiency, but you have a much more stringent limitation, which occurs because the semiconductor are not perfect. In other words, electron hole pairs that are generated in a solar cell may not reach the contacts to provide current or power, right? They might get trapped within defects in a semiconductor. So that means that photovoltaics, for instance, can at least, it's extremely difficult for them to reach something like a Carnot efficiency. And we'll talk more about this when we talk about solar cells in detail. Same thing happens when you do photosynthesis, light to fuel. In fact, photosynthesis is a very, very low efficiency process, even though it's ubiquitous in nature. You have the same sort of situation where you're creating electron hole pairs, but now in organics, which have much lower conductivity. So you can see that these things are much less efficient than photovoltaics. But in any case, in all the situations, thermodynamics essentially places the upper limits of conversion efficiency. And that's basically determined by this particular equation, which is a Carnot equation. So let's see this in some basic ideas. So basic thermodynamics, as what we need to think about are two laws. The first law of thermodynamics is essentially an energy conservation law, which basically states delta U equals Q minus W. Delta U is, so when you talk about thermodynamics, usually we think about these as closed systems, okay? Not necessarily completely closed, but you think about the energy in a system. And that system can be a solar cell. It can be, for instance, a solar cell and the sun, or it can be a heat engine, whatever. So the change in internal energy of the system, which is delta U, is given by the heat added to the system minus the work done by the system, which makes sense, right? So you have the heat coming into the system. Work is essentially work done by the system, so that leaves the system, and delta U is the change in internal energy of the system. Okay, now, of course, delta U can be negative, so just keep that in mind as well. The second law of thermodynamics is a little bit more abstract. It says that entropy, delta S, is always positive. So in other words, the change in entropy is always positive. In other words, entropy is always increasing, or it remains the same. This is a very, very fundamental law. In fact, this is the reason why the whole universe is expanding. Entropy has to increase. And there are some very fundamental reasons for this, which we will go into, but this is essentially the reason. For instance, in the internal combustion engine, when you have the explosion of the fuel-air mixture, it's the reason why the piston actually expands. I mean, the gas actually expands and the piston moves, right? The entropy is actually increasing. Less important for us, except just from a conceptual point of view. Now, how do we apply these laws in order to think about heat engines? How do you apply this to heat engines? Now, of course, there's quite a bit of mathematics which goes into how to derive the limitations of heat engines, but we will look at this from a very conceptual point of view, okay? So the way we'll think about it is as follows. So let's look at this very simplistic model of a heat engine first. Again, as I said before, there is a hot region, and then there's a cold region. Okay, and the hot region is typically referred to source. The cold region is referred to as the sink. Heat. Is there a question? Sorry. No.
No, I guess.
Okay, so the heat comes in from the hot region, which, by the way, so again, this is a very abstract concept here, but think about this, for instance, as the absorber from a concentrated solar light. So for instance, you have a big lens here collecting sunlight, and you're heating up some spot here, right? So, but we are generalizing everything by looking at a very abstract concept here. So a hot region which puts in heat into some engine that does work, okay, W here, and it loses some energy as Q out to a sink. Okay, so from the first law of thermodynamics, we know that Q in should be equal to Q out plus W. Okay. Now, what Carnot's theorem states is that all irreversible heat engines between two heat reservoirs are less efficient than a Carnot engine operating between the same reservoirs. Okay, what does that mean? That means the best possible efficiency of an engine, a heat engine, that one can hope to achieve is determined not by the details of the engine, but by only two numbers: the temperature of the hot part and the temperature of the cold part. So that's a very profound idea, right? In other words, you can think about the heat engine as a black box. You don't really care what is happening inside. As long as I know what the hot temperature is and what the cold temperature is, I can predict, okay, this is the best efficiency I can hope to achieve is given by those two numbers. So of course, we're not going to prove that theorem, but that's a very, very powerful idea. So in other words, you can actually compare many, many things across many disciplines without actually knowing the details of what's going on inside. Now, of course, this just gives you an upper limit for the efficiency, but Carnot also proposed a heat engine that allows you to achieve this efficiency, at least conceptually. Okay, and so let's look at that. And this is referred to as a Carnot cycle. So the Carnot cycle essentially is the maximum possible efficiency of a heat engine. Okay, so let's zoom in here and take a look at what this is. So these are very common ways of design representing what happens inside a heat engine again in a very general fashion. So the horizontal axis here is volume. So this is typically talking about a gas in a chamber. Okay, so this is the volume of the gas, and this is the pressure of the gas. So for instance, think about the internal combustion chamber where there was gas that was being heated up, okay? So let's start at this point of the curve. So this is a curve, right? Pressure volume curve. And let's go through, follow this curve along this line here, shown in red, okay? This is a situation where the heat is coming in. So this is the heat coming into the system. So we are here, okay? We are inside the chamber, and the volume is increasing, right? It's going in that direction. The pressure is decreasing because the gas is expanding as it gets hotter, okay? And here in Carnot cycle, which is an ideal situation, this red part of the curve is referred to as an isothermal expansion, which means that the temperature does not change. So the temperature is fixed at the hot temperature, TH, but the gas is simply expanding. Okay? That's the red part of the curve. The blue, the next step that happens is referred to as an adiabatic expansion, which means that you are essentially expanding without doing any change in the PV, pressure volume product. So it goes as like that, okay, following this blue curve here. Okay, so now it's expanded to the maximum. So of course the temperature has changed because now you're in the cold part, okay? And then so that it's at TC and right here at this point, which is the cold part. Then you have isothermal compression. So for instance, the piston is pushing in and compressing the gas, which goes up. So as you compresses, the volume decreases. So the curve goes down like that. Okay, again at a fixed temperature. And at this point, of course, because the gas is being compressed, it will lose heat. It's very similar to the refrigerator we saw, right? So heat goes out into the cold sink. Then you have an adiabatic compression, which happens here, which brings it back to the original state, okay? So it's a cycle. So the cycle repeats itself, right? Goes like that, like that, like that, keeps going. The work done by this cycle is represented by the area under all these curves here. Okay, that's shown by this red curve right here. And that net work W is the area inside the PV curves. So if you think about the system, you have heat coming in, heat going out, which is this Q in and Q out, and the work done, which is the area under this curve. What Carnot's theorem says that the work done divided by Q in, which is a heat in, it cannot be higher than this number right here, Carnot efficiency, which is TH minus TC over TH, or 1 minus TC over TH. Okay. Now there are many other kinds of heat engines as well. Okay, it doesn't just need to be Carnot. There's something called a Stirling heat engine. We'll look at that briefly here again. The only difference here compared to the Carnot is that the cycle is a little bit different. You know, here you have essentially a constant volume increase in pressure, and here you have the expansion, and then you have a constant volume decrease in pressure expansion. This is something called a Stirling cycle. And Stirling cycle is actually fairly commonly used in solar thermal applications, which you might see if you work on. We will see in some of the future lectures as well. So again, these are constant temperature curves here. TC, constant temperature T. Okay, not terribly important, but it's useful for us to understand the basic concept here. Now, Carnot's theorem also implies that all reversible heat engines between two heat reservoirs are equally efficient with a Carnot engine operating between the reservoirs. So let me turn off my Slack because my students are messaging. Sorry about that. Let me close that. Okay. Into that. Okay. So what I'm saying is that if, again, this is just reiterating what we saw before, that any reversible heat engine is, if you want to know its maximum efficiency, is determined by the temperature of the two heat reservoirs, and that's it. Okay. And this is essentially a consequence of the second law of thermodynamics. So it's very, very fundamental. You cannot overcome, just to keep in mind. So let me give you a good example of why this is important. So if someone tries to tell you, okay, I have made a solar cell which is 100% efficient, you know that's not possible because of the second law of thermodynamics. The Carnot's theorem says that. So let's think about solar cells for a second. So in the case of the solar cell, the source is of course the sun, so that's the temperature of the sun. The sink is of course the solar cell, is the temperature of the solar cell, 300 Kelvin or so, right, on Earth. There is a maximum that you can get, right? 1 minus TH or TC, TC over TH will be some number, but it's not going to be 100%, right? So it tells you that, for instance, the solar panel can never be 100% efficient. In fact, we will look at this in some detail later on, but just keep that in mind as well. Now let's do a particular example to make sense of all these concepts, okay? And this is a useful way to think about it. Let's think of, and because this is common for almost all the teams in the project, let's think about the efficiency of a solar collector, okay? And this collector can be for hot water, desalination, pasteurization, or photovoltaics. We don't care what it is. We're just going to generalize it, okay? So we know the efficiency represented by eta Carnot. The absolute efficiency limit is 1 minus TC over TH. So that's the efficiency of our heat engine, assuming it's a perfect heat engine, okay? The efficiency of the collector, which is eta collector, is given by the amount of energy that's absorbed minus the amount of energy that's lost divided by the energy that's incident on it, okay? It's obvious. So let's first think about what's incident. So let's look here. Let's skip this for a second. This is easier. The incident power is very simple. It's simply the area of the collector multiplied by any concentration factor you might have. So you might use a lens to collect more light. So let's put a concentration factor here. That's a simple geometric concentration factor. So the consequence of the C is that A times C is the effective collector area. So if C is a 10, that means you're collecting light over an area that's 10 times the area of the collector, right? So that's the definition of concentration. So we'll again see this again and again in the future, but just think about this concept. And of course, that's the effective area multiplied by the incident solar intensity. Okay, that's the radiance in watts per meter squared. Okay, that's what we saw in the last lecture. So that's the total incident power. The power that's lost is also related to our last lecture, which is basically Stefan-Boltzmann Law, because this solar collector can be thought of as a black body, right? So we know a black body that absorbs energy also has to lose energy by radiation, and the amount of lost energy by radiation is simply given by the area of the collector multiplied by some constant term that's less than 1. It's referred to as emissivity. In other words, how close to a black body is the collector actually? If it's a perfect black body, this number is 1. If it's a non-ideal black body, this number is less than 1. And then we have the familiar Stefan-Boltzmann law, which we saw in the last lecture. Sigma, which is the Stefan-Boltzmann constant, times T raised to 4, where T is the temperature. In this case, the temperature of the wait a second, this should be the temperature of the collector. This is the temperature of the hard body. Okay, so this is a typo. I'll correct it. This H should really be C. Okay, so only radiative losses. So you put them all together. So so the last term here. So again, remember, we are trying to compute the efficiency of the collector. So we have done the losses, we've done the incident power. How much is absorbed? How much is absorbed? We're going to assume that everything is absorbed. Okay, so it's an ideal collector. In other words, everything that comes in is absorbed. So Q absorbed is now equal to Q incident. That makes our equation simpler. So eta collector simply becomes 1 minus Q lost over Q incident, or it becomes 1 minus this term here. Epsilon, sigma, T raised to 4, again, this should be C, divided by capital C for concentration, nice solar, which is the incident intensity. Okay, get a fairly simple equation. AC is the collector area, A is the absorber area. Okay, we saw that. So the total efficiency of the system now, which can be thought of as eta, is the collector efficiency multiplied by the heat engine efficiency, right? And we didn't say what the heat engine is. We don't care. It can be photovoltaic, can be solar thermal, whatever. You just multiply them together. Put them together, you get this equation. So the system efficiency now, again, this is the upper bound. This is the maximum possible system efficiency. It's a Carnot efficiency given by there, times the collector efficiency, which is given by this. Okay, now this is very interesting because you can see it depends on the temperature of the collector. The temperature of the sun you can't really change, so that's fixed. Depends on temperature of the collector. It depends on all these things you cannot change, they're constants, right? Depends on the concentration factor, which you can change, and depends on the intensity of the sunlight, which you cannot really change. Okay, so then that's shown in this plot here. So this plots the efficiency, again, the maximum possible theoretical efficiency as a function of the temperature of the collector. Okay, for many curves, and these curves represent different concentration factors. So let's look at this black curve here for a second. So the concentration factor is 10. Okay, temperature goes from 300 Kelvin, which is room temperature, let's say, to roughly twice, almost 650 Kelvin. So first of all, you'll notice as you increase the temperature of oh, sorry, this is the hot source temperature. So if when you increase the temperature of the hot source, the efficiency increases, right? As you increase that, this number goes up, this whole thing goes down, and this whole thing goes up, right? So the Carnot efficiency increases up to a limit, after which, because of the losses starts dominating, and it starts going down. So it reaches a peak value here. Okay. Now what's very interesting is you can increase the peak value by simply increasing the concentration. So the higher the concentration, this curve starts moving higher and to the right. So this is a good example of why you would want to use concentration, because you can get higher efficiencies. And we'll see this in a different context when we talk about concentrated photovoltaics. Because you will see that when you do concentration, you will also end up with an advantage because you're creating more current density. So you'll be creating more electron-hole pairs. Okay, so this is just a very simple example showing you how to apply some basic principles of quantum mechanics to understand the limiting efficiencies of any system, and in particular for solar systems. Now let's look at a few examples of where these things are applied. Most obviously, these are applied in solar thermal plants. And there are two examples shown here. You can have a solar thermal plant that's somewhat distributed. So you basically have a dish-like setup, okay, which is a parabolic dish, and collects the sunlight, but it's still huge, relatively huge. And then it has a little heat engine at the focus, okay. I say little because these things can essentially be repeated, right? You can make larger arrays of these. And this is, for instance, something from Sandia National Labs called the Sandia Dish Stirling Engine. In this particular example, they're using a Stirling cycle here. The max efficiency for this whole system is roughly 30%. They have a concentration of 2000, so it's pretty high concentration. Operating temperature is very high, 700 degrees. There are relatively large installations, mostly in the desert southwest. Roughly, they can produce about 25 kilowatts peak per dish. And of course, you can also see this parabolic system has to track the sun, right? So it has a fairly complicated two-axis tracker as well. The other alternative option for solar thermal is shown here. And this is a very, very elegant solution where all you do, and we'll see this in more detail, this is called, by the way, called a power tower. This is an example from Spain, where you put a whole bunch of mirrors on the ground, and you ensure those mirrors are oriented in such a way that the light is always pointing to a target up here on top of this tower. So you use this huge area, so it's a highly centralized system, with lots and lots of mirrors, thousands, tens of thousands of mirrors, all of them pointing sunlight to a target. And this target, of course, gets really, really hot. So that's our hot region. And from that hot region, you can actually run a heat engine, run steam, whatever. We'll see some examples. So these systems can be huge. They can be very large. So this one of the larger systems is a 11 megawatt peak power plant running at 250 degrees Celsius steam turbine. Okay, but the very largest plant like this is actually located not too far from us, near Las Vegas. You know, we'll see a short video about that, which is very interesting as well. So yeah, so the thing, last thing I wanted to show you are two examples of the solar towers, and I want you to look at these two examples and spend a minute or two basically discussing and brainstorming and telling me what you think are some of the problems. So when you see the videos, try to think about what are the most obvious or not so obvious problems for these systems. And I emphasize these systems because these systems in general tend to be fairly high efficiency, and in terms of I would say not just high efficiency, but in terms of cost. If you think about the total cost of power, they give you a pretty good value compared to, let's say, roof-mounted, homeowner roof-mounted solar panels. So that's why these systems are important, and it's important for us to consider them. So let's first look at the solar tower in Spain. And this is a very unique system because it has storage, which means that this is a power plant that can produce full 24-hour electricity. So in other words, during the day, it can produce electricity, obviously, but during the night, it can also produce electricity because it actually stores its energy underground, and we'll see how that works. So let me try to play this.
The problem with renewable energy is the lack of continuous supply. Solar power only when it's sunny, wind power only when it's windy, and wave power when the sea's not too rough. I'm Russell Beard and I've come to South Spain to visit Gemma Solar, the first solar tower power station that can produce electricity 24 hours a day. But in order to get a real sense of the scale of this place, I need to get a little bit higher. Samuel! It's incredible. I can't believe I'm flying this place. Sam just spotted the tower up ahead, so he said just point at the tower and carry on. Okay, here is Gemma Solar. You can see it just below us now. Thousands of these heliostats, these revolving mirrors. It's just amazing.
So I should point out each of these mirrors is called a heliostat, and we'll see more and more of this. But one thing very interesting you will notice is just in this picture right here, you will see they're arranged not in a concentric circles, right? If you look carefully, now you see there's a break there, there's a break there, and so on. And the way these are arranged is very, very, very carefully calculated in order to ensure many things. But for instance, you want to reduce the cost of the system by reducing the number of mirrors that is used. You also want to make sure you have as much coverage as possible so you don't lose light. You also want to ensure that the solar panel, these heliostats don't shadow each other, right? They cannot be too close. So it's a very complicated system. But one thing you would appreciate by looking from above on this is that it kind of looks like a sunflower, right? You will notice this actually is inspired in a sense by nature, because nature does something very, very similar for its flowers and leaves and so on. Okay.
It feels like we're looking into the future. Photovoltaic is like one of the fastest growing energy sources in the world at the moment. But these aren't photovoltaics, are they?
No, they're not photovoltaics at all.
So these
Those
are just
glass, are mirrors, and they are reflecting the light on top of the tower.
reflected sunlight from the 2,650 heliostats combined can generate enough electricity to power 25,000 homes, but only if they're all pointing in exactly the right spot. Santiago's brought along one of these miniature parabolic mirrors, which I guess is almost like a perfect scale model of your solar tower.
Yes, I mean, the tower looks like in the middle of a circle of heliostats, and every heliostat is like, taking a different angle to reflect the light on top of the tower, and then to concentrate all the energy on a single spot.
So let me try.
Oh, yeah, it's fine, it's fine.
Oh wow, you can see it catching fire. It's so sensitive, like one tiny degree out and it stops burning. I mean, this must be the challenge that you're facing.
Exactly. I mean, exactly what we have to be doing. I mean, we have to be very precise in moving the aerostats in the right position to concentrate the light there.
Sunlight is reflected from each rheostat onto a central receiver at the top of the tower. Sodium and potassium nitrate salts are pumped from the cold salts tank up to the receiver, where they absorb the concentrated solar thermal energy, reaching temperatures of up to 565 degrees. The heated salts are then pumped down to the hot salts tank, where they can be stored in a molten state or used to generate electricity via the heat engine.
This is the hot molten salt tank that contains the molten salts at 565 degrees. This is like a big battery, but it's a thermal battery. It's not an electrical battery. In fact, the energy which is accumulated here is enough to continue operating the turbine for 15 hours at full speed.
So this is what distinguishes this place from other solar tower generators around the world. It's actually that storage.
Exactly.
Being able to store energy this way means the solar power can, for the first time, be provided 24 hours a day, not just when the sun's shining.
This is the vessel in which the water becomes steam. Inside you have water at maybe 500 degrees centigrade and already 100 bars of pressure.
This is incredible. So what Santiago's telling us is, despite how futuristic this all looks, the actual business end where they create the electricity, much the same as any other coal-fired or even nuclear power plant. So see, it's a steam-driven power plant. Wow, this is what I'm talking about. And this looks like the power station. This technology has been around for hundreds of years. Yeah. So it's really out there, it's the only sci-fi part of this building. By the time the power comes down from the molten salts, we're talking about good old-fashioned steam turbines. That's what we can hear now. And you can even see it, that little chimney at the top.
We are going to be reducing our costs, but also due to the fact that the oil prices are going up, will make it possible to burn gas to produce electricity. And then,
okay, so you get the idea here. Now let's look at a slightly different plant, which is the one that's closest to us. It's called the Ivan Power Plant near Las Vegas. In fact, if you ever drive to Vegas, it's a little bit, I would say, southwest of it, and it's actually quite incredible to see, and more interesting if you ever have a chance to fly from Salt Lake to, let's say, California or somewhere in the southwest. You can actually see that it's incredible. So let's take a quick look at this, because this is very relevant to in our neighborhood. And short, it's from a company called Bright Source. So you can see it. Now, you see there are two mirrors for each heliostat, and there's a reason for that, obviously, because there are two axes tracking, right? You want to use one mirror to track the other side, and use the other one to track on the other axis. You can either move them separately or together, so it gives additional control. And you can see that the region is not flat, right? It has some topography, and the mirrors actually compensate for that. So it's a fairly complicated controls problem, right? There's huge computation involved in optimizing. And it's huge, so it's almost 400 megawatts. So it's a pretty large plant. There are three of them, as you can see. And it's important, the cooling method is of course quite important because it's in the desert. So it's desert. This particular system doesn't use a lot of water. So air cooled. But of course, this does not have storage like the system in Spain. So if it's at night, it does not produce power. Of course, if you can combine this with huge batteries, then that problem can be avoided, right? Okay, so I think that's basically. So let's take a minute or so, kind of think about what are the main problems with this with these two approaches. So I want to spend like roughly a minute before we end. Can anyone think about some problems with these systems? You can just discuss in between yourselves, or just speak loudly so I can hear it.
Weather.
Say it again.
Weather.
Weather, you mean if it's cloudy?
If cloudy, rain, snows, dirt, whatever.
Yes.
Mirrors clean.
Yes, that's a very, very good point. So, of course, that's why they choose these locations, like in southern Spain or southwest United States, where we don't have much rain, right? You don't have too many cloudy days. That's why they use those locations. But you did raise a very, very important point, which is dirt. Now, if those mirrors get dirty, and they can, right, because they're in the desert, they don't, their efficiency goes down. Think about it this way, right? If your mirror is 90% efficient versus 99% efficient, you are losing huge amount of energy because you multiply that loss by 100,000 mirrors. So it's a big deal. So that means the maintenance costs are pretty high. That's one. Anything else? So in other words, someone has to go, or some robot has to go and clean the mirrors periodically. Anything else?
You mentioned the complexity of aligning all the mirrors, making sure they're all aligned, and calibrating those and making sure they're aligned. I'm sure that is something, a consideration over time. You're going to have to continually have maintenance in the right direction.
You mean the position of the sun? Is that what you mean?
Yeah, position of the sun, but also just the mirrors themselves. Because I'm guessing, right, there's mechanical, like they're tracking the sun, and that mechanical part of the mirrors that moves. You're going to have to. There's going to be some maintenance.
Yes, yeah, good, very good point. So the two issues here, one is, of course, the sun doesn't necessarily follow the exact same path every year, right? Changes. Fortunately, astronomy is so advanced now that that's relatively easy to predict. The second problem is more severe, I would say, is the fact that this is a mechanical tracker, right? Those things have to mechanically move, and we all know that motors essentially die, right? If they get dirt, dust, whatever, and over time they just die, right? So they need to be replaced and so on. So it's expensive. Again, adds maintenance. So we'll come to this issue of mechanical tracking later on in this class, and think about other ways to track the sun that are non-mechanical. So a good example is, how does the sunflower point towards the sun, right? Can we gain inspiration from that? Any other issues with this?
I'm sure the process of deciding on a material for the top of the tower is pretty difficult. You want like maximum thermal uptake with minimum radiative loss.
That's true, which is why the focus of those things are relatively small, right? The region that's super hot is small, because you want to keep the surface area very small. Of course, that also means that you need to focus these beams of light very precisely. So you're right. The smaller you make it, the better it is in terms of losses, but it gets more challenging in terms of focusing. So you're correct, yes. But I would say one of the most important problems with system is environmental, right? So you need a huge area here. You're talking, especially if you want a very large system, and these areas are not, they're not, they are fairly fragile, right? You have fragile desert ecosystems and so on. So it's a big challenge, I would say, from that point of view. Other things like birds and so on, if it's these things are very dangerous, obviously. So if some birds come even in the close vicinity, they'll die and so on. So lots of issues here. from those point of view. And technically, of course, you can think about other things as well. How do you build such systems in fairly remote environments where this tend to be, and how do you make sure you can transport electricity efficiently from those environments to where the customers are. Okay, so in the interest of time, I just wanted to, this is the last slide. As I said, I will stop a little early today. But just to remind you, and I want you to take the rest of the 10 minutes or so you have remaining to meet your team members and discuss your assignments, okay? Because I don't want you, I know everyone's busy with other classes, but that's why I keep nagging a little bit. So keep in mind the assignment 1 is due next week. Assignment 2, I will publish it next week. I don't want to overwhelm you. I want you to make progress on 1, so that's why I'm holding off. But the goal of assignments 1 and 2 is to help you with your presentation 1. So all of this will help you, right? It's not a waste of time. So just think about it that way. Presentation 1 is, of course, due September 28th. And this is important because it counts towards your grade significantly. And the key part of presentation 1 is your innovation. What problem are you solving? You need to do a brainstorming session, or 1 or more, where you essentially have to sit with your team, and it can be remote, it doesn't need to be in person, where you have to list your ideas. I want you to show the results of your brainstorming session. In other words, I want to see all the ideas and how you chose a few to pursue. Okay, so this is a very important exercise I want you to take at this very early stage of the project. Okay, so for the presentation format, because we have about 5 teams, we will limit to 10 minutes and about 5 minutes for questions and answers. And the entire class will be expected to ask questions, so make sure you pay attention and ask questions. Okay, any questions about this and anything about the rest of the lecture as well? Because this is my last slide and we'll stop here. Okay, I guess not. So again, just to remind you, if you have any questions or concerns, just email me or email the TA. We are both available all the time for you. So I'll respond pretty quickly if you have any questions. So. Great. All right, I guess I'll see you all next week then.